and I'm also the chair of the chemistry department. And if you're in this session, you should be here to um, hear about a chemistry program, and there are a number of them, including nanoscience and nanotechnology and toxicology. And the food science program is also housed within the chemistry department. So I'm going to talk about that as well. I see a number of you online now. Let's see, mostly from Canada. Oh, one from Colombia. Welcome from all the way there. Another one from Dominica. So welcome to all of you. I hope you find this interactive and useful. If you've got a question during the presentation, just throw it in the chat. I'll stop at any time to answer questions. You don't have to wait until the end of the presentation. So as I said, I'm going to discuss a number of programs which are all housed within the chemistry department. But I want to tell you something about the department itself. That's housed in the Stacy building, which you can see here. It's comprised of 2 administrative staff, sort of office staff, 10 technical staff. They take care of the laboratories and the equipment. 22 faculty members, people like me, the teachers for the most part, which include a number of categories of professors, instructors who only teach, assistant, associate, and full professors who teach and do research. We have 5 professors emeriti. These are professors who worked here for probably their whole lives and have now retired, but are still very active in the field. And so we keep them on staff to do various things, such as teaching and examining students. 9 adjunct professors. These are professors who are outside the department, but have a research collaboration with us. There's a lot of research going on in the Ottawa area, as you probably just heard from Nadine. And so the adjuncts are in various locations in the city. Our programs comprise about 200 undergraduate students across all of the programs that I mentioned, and about 55 graduate students who are doing research here as well. I want to tell you right off the bat that we're a research-intensive department, and involving you in research is something that we are absolutely bent on doing. We try to involve students in research right from the get-go. So many students are working in our labs immediately after first year, often in the summer between first and second year. And they continue to do that, sometimes during the academic year, but sometimes you're a bit too busy to do that, but often during the summers between academic years. So you can see the areas that we're doing research in here, everything from analytical to toxicology, including food science in the middle there. And nano stuff, nanotechnology, and nanoscience are a specialty here. And I'm going to talk in more detail about those, and about food science, and about toxicology. What chemists do and why chemistry is chemistry can really be summed up like this. We make stuff. And that might sound a bit silly, but we make things that never existed before, at least as far as we know they don't exist anywhere else in the universe. So we do this not sort of haphazardly. We don't just sort of add A to B and see what happens. We purposely try to make new molecules that have functions that we're looking for. And we do this using theory as our guide. So the theory is what you learn in the various courses in a 4-year program. And going into the lab and making these molecules puts that theory into practice. So this is quite different from, a biologist who probably studies what nature has given us, but really doesn't create new things. I mean, maybe they created vaccines, didn't they, which was a pretty big deal recently. Or engineers who build a bridge or something like that, but they've done that before. When we make a new molecule, it's with a specific purpose in mind, and that really sets us apart from other fields. And this is so important because everything that you can see or touch or taste or feel or hear is composed of chemicals. And so advances in technology and medicine, for instance, are built on chemistry. The cell phone that you might be watching this presentation on, solar power that might have charged up your cell phone in the first place, disease detection and treatment, pretty big field these days. Environmental protection, this is enormous. You've probably heard about the COP conference going on in Glasgow at the moment. Pollution detection and environmental monitoring are based on chemical analysis. Development of cleanup strategies as well. Alternative materials. What's a good example? Cars these days are made not so much of steel, they're made of carbon composites, for instance. So this is all in the domain of chemistry. And this is why it's such an interesting field, because there's a fundamental backbone to it, but there's a very practical reason for doing it as well. Skills that good chemists have, and you will be a good chemist if you come here, are, first of all, the knowledge of chemistry. And that's composed of both theory and laboratory skills. You have to understand what you're doing, then you need to go into the lab and be able to carry it out safely and effectively. You need to have good written and oral communication skills, because once you've invented something, you've got to get out and tell the world what you've done. You need to have critical thinking and problem-solving skills, because a problem in chemistry is not a multiple choice problem. It doesn't come with 5 answers, one of which is right. It's just a problem. You're presented with it, and you've got to use the skills that you've learned during your education to solve it. Now, chemistry is often called the central science, and we're not being big-headed when we say this. We say this because chemistry is so connected to the other fields and connected to so many other fields that it really is a central science. You need to have some math and stats background, and it doesn't have to be a crazy amount. You don't have to be a truly gifted mathematician. My math is pretty strong, but other people's skills don't include, chemist skills don't include a whole lot of math, because they do a type of chemistry that doesn't require it. But you do need some. It's very much connected to physics, and you might say, but I don't want to do physics. I don't like physics. You don't have to do a lot of physics. If you do physical chemistry like I do, then you need more physics and more math. But if you do organic chemistry, you need far less of it. Biology and biochemistry very, very closely connected to chemistry these days. In fact, in some cases, it's difficult to differentiate. Am I a biochemist or a biologist, a molecular biologist, or am I a chemist? They're very much connected. Business and economics, and you might be thinking, what's that got to do with chemistry? It's got everything to do with chemistry. If you've invented something, now somebody's got to get out there and sell it. And if they don't sell it, well, it was kind of a useless invention, wasn't it? So we at least give you the opportunity to learn some business and economics. Ethics is a big deal in chemistry. I mean, you can't just do things willy-nilly and pollute the environment and hurt people and so on. So ethics is a big deal. And more we tie our programs, especially food science, as I'll show you momentarily, to policy issues. You need to be able to work and learn independently. In other words, you have to hand in your own work so we can judge how much learning you've done. But you also need to learn to work and learn as part of a team, that should say, because so much of what's done in a chemistry laboratory is sort of a team sport. These are giant projects, and you're going to have your own little subsection of a project when you're doing research, but you have to understand that you're contributing to a larger research program and a larger research effort in the department. So you have to work as part of a team as well. So here are some of the programs that you can take in chemistry. You can take straight chemistry, and that's where most of our students are. You can take a combined computer science and chemistry. Those two go very much hand in hand. You like both of them, you can't choose. Choose a program where you can do both. Likewise, chemistry and earth science and chemistry and physics. These are combined honors programs, which are roughly half of each. So in chemistry and physics, half your courses would be physics and the other half would be chemistry. These programs don't leave a lot of room for optional courses, because the chemists want you to take the best chemistry courses and the physicists want you to take the best physics courses. So your program's pretty hardwired. But these are excellent programs for people with big brains. We have a concentration in nanotechnology, which I'll talk about a little bit now. This is a chemistry program with a concentration in nanotech. Down at the bottom, you see nanoscience, which is certainly related to nanotech, but this is a joint program between chemistry and the electronics department on campus. We have a concentration in toxicology. That's a fairly new program. And we have a fairly well-established food science program, which is not technically a chemistry program, but it's housed within the chemistry department. So that's why I'm talking about it. today. People are often, I'll come back to the details of the programs, but people are often asking, what about scholarships? How much money can I get to take a little bit of the heat off tuition? Well, there are entrance scholarships, and I think the dean may have just talked a little bit about these, so I won't dwell on them. Depending on your average in especially your grade 12 courses, the award depends on that, and if you're up in the stratosphere, 95 to 100%, in grade 12, well, that's $4,000 a year, and it's renewable every year, which I think somebody also said in the other session. That distinguishes Carleton from most universities. There are a bunch of prestige scholarships as well that you need to apply for, so-called chancellor scholarships. $7,500, that pays your tuition entirely. About 40% of entering students hold scholarships, and we give out a lot of them because we know that most of those students will lose them after first year. They take a bit of a hit, they drop down into the 70s, they lose their scholarship, but if you do well in second year, you can get it back in third year. That's entirely different from almost every other university. So you have to maintain an A- average 80% to retain scholarship. There's an average drop in grades going from high school to university of about 12%. So if you were a 90% student, all of a sudden you're a 78% student and you're thinking, I'm going to fail. You're not going to fail. You're going to get back on your horse and your grades are going to start to increase in second and third year again. They're also in-program scholarships, and I'm talking about these here because these pertain only to students in the chemistry department. And there are a number of them listed here. These are so-called endowed scholarships. These individuals put in some money years ago, and that money has grown to the point where the interest pays a number of scholarships. So there's some pretty eminent scientists in here too. Alison Flood, for instance, was a preeminent scientist at the National Research Council here in Ottawa. So a number of these are available as well. Chemistry also has a co-op program, as do all science programs, but I want to highlight that this is the case. You have to have 80% in your grade 12 4U credits or equivalent to get into the co-op initially, and you have to maintain a B average in your university chemistry courses. Not the other ones, not the arts courses or whatever else that you take, but in your chemistry courses. So why would you do a co-op degree? You get experience. You get to see a potential employer. They get to see you. These often lead, these placements, to jobs after your degree is over. They typically pay a little better than other summer jobs. Tree planting pretty hard on your back, and it's only a pennies a tree. If you're going to be a chemist, why not get into a lab after first year or after second year? The co-op actually starts after second year. And so this is something that you can consider. We don't have a lot of students in co-op because they can also find jobs in the Ottawa area in chemistry without being in co-op, but it's one way to do it. If you do a co-op placement, or if you find a job elsewhere, you'll find that there are lots of opportunities in Ottawa. Here are a number of examples of places where we have placed students. So first of all, you'll see a number of government labs: health, environment, natural resources, nuclear labs, and the National Research Council of Canada, which is mostly in Ottawa. So a lot of placements there. That's a huge asset of Ottawa, a huge benefit of being in Ottawa, all these government labs. But a lot of other companies, Iogen is in town. They make fuel from biomass. The RCMP forensic labs, main forensic labs are here. EPOCAL is a small biotech firm, and so on. So there are many firms in Ottawa that can host a co-op student. How difficult is it to be here, and what might you expect? So I want to give you a few things about the transition to first year. I know that they spoke a little bit about it in the dean's session, but I'm going to speak a little bit more about it here. That transition from high school to university is a substantial one, and some people navigate it very well, and some have a bit of difficulty, but then get on their horse in second year. So you're coping with maybe new independence. You haven't been away from home before. Freedom, you might call that. New relationships with people, and so on. You're coping with an intellectual demand of course material, which is I've put it as modest here, but for some people it's a little higher than that, depending on what kind of high school education you got. The idea is that in first year we bring you all up to the same level, higher than it was in grade 12. And then in second year we introduce the more demanding material. So, but in first year I would say the intellectual demand for most people is modest and the volume of work is modest. Second year, it is tougher, no doubt about that. Everybody's at the same level. Now we whack you. We give you all kinds of new material, and we give you, so I would call the intellectual demand moderate, and we give you an enormous load of material. This is not uncommon in any science program. First year, you're all brought up to the same level. You've got some basic skills. Second year, now the rubber hits the road. In second year, if you're in an honors chem, you'd take 7 chemistry courses, 6 of which have labs. In third year, the intellectual demand of the material is probably the highest. You know a lot after 2 years studying chemistry, so we can hit you with some more advanced material. The volume of work, still moderate, I would say, or maybe a little bit lower than it was in second year. And then in fourth year, you'll find that it goes by just like that. And this is because you're into what you're doing. You're taking more of what you like and less of what you don't like. You don't have to take any more arts credits or physics courses or whatever it is you don't like. You're probably just taking chemistry courses by fourth year. You're also doing your fourth year research project. So you find that that just disappears. The intellectual demand of the course material, again, is moderate, and this is because you're better at what you do now. You want to take organic chemistry for the rest of your life? Well, great, you take more of that in fourth year. So the intellectual demand is lower on you. And the volume of work, I would say, is moderate to high, but your brain is much bigger by the time you get to fourth year. You can handle it. Let me show you what a typical first year in chemistry looks like. You'd take 2 halves of general chemistry, 2 halves of general physics. You've got some choice there, but you got to do 2 courses, one in the winter, one in the fall, one in the winter. 2 maths, a calculus and an algebra. You've got to do another science, and for chemistry students, that means probably biology, computer science, or earth science. You've got to do an arts or social science course or a seminar in science. They may have spoken about this in the dean session as well. But that's a small course, or a course with small sections of only 30 students. So you get to know your fellow students. That's highly recommended. You don't have to do that course, but we recommend it. In nanoscience, now this is the joint program between chemistry and the electronics department. You still have to do 2 courses in chemistry. You still have to do 2 courses in physics. You have to do a 3rd course in math, an arts, and a free elective. So you'll notice the program in first year isn't all that different. And I know they said this to you in the dean session, but I'll say it again. If you get to the end of first year and you decide, I shouldn't be in nanoscience, I should be in honors chemistry, you can switch without any penalty. You'll bring all your credits with you into the new program. The longer you wait to switch programs, the more difficult it gets. Here's a first year in food science. Chemistry, physics, math, sound familiar? Biology, sound familiar? A first course in food science, and 2 courses in economics, because those are so pertinent to what a food scientist does. So I want to delve down into some of these programs in detail, notably the ones in black here. Food science, nanotech, nanoscience, and toxicology. The other ones that are in red are encompassed by a general program or honors program in chemistry. But the ones in black are separate programs with separate requirements and separate outcomes. What's a food scientist do? Well, they study the physical, chemical, microbiological, biological aspects of food. And depending on what direction they go, they may develop ways to process or preserve food. They may develop ways to package or store food. And all of this is done in accordance with fairly strict government regulations. So we've got pretty strong liaisons with the Canadian Food Inspection Agency, which is based in Ottawa, and with Health Canada, which regulates the food industry. And you may not know, but it takes a lot of work and money, resources, to make a food product. So if you want to make this orange drink, whatever this happens to be, there's got to be some basic research. So that's the guy down in the lower left corner here, and maybe this fellow in the bottom. There's got to be some engineering. So on a larger scale, this is a scaled up many liters. Here's a factory producing this stuff. There's got to be some sensory evaluation, consumer satisfaction testing, and so on, until finally there's a product which you can put on the shelf and market. So there's a lot of science in that. And it just takes a lot of work to do that. It's hard to appreciate when you just snap open a bottle of some prepared food and chug it down. But an awful lot of science went into that. What kind of jobs do you find in food science? And I can say this from experience that we know these are the jobs that are available because our graduates have written back and said, here's what I do. I'm a product development scientist. I'm a microbiologist working in the food industry, very important part of the food industry. Keep those bugs away from your food. I'm an analytical chemist. A lot of analysis of food goes on. I'm in operations or marketing or quality control or quality assurance or what have you. So our graduates are extremely successful coming out of this program. What they are not are nutritionists and dietitians. Food science is not nutrition, and it's not dietetics. We do teach some of those, especially nutrition, but you will not be an accredited nutritionist coming out of this program. You'll be an accredited scientist, food scientist. I want to impress upon you, I hope the characters aren't too small here, but how broad this field is. So these are all of the food courses that we offer. You have to take about 2/3 of these, and then you have options among the other 1/3 or so. You've got to take all the ones up to the 3,000 level. So there's some intro courses. There are immediately in second year some courses on regulation and in the Canadian food industry. This is something that distinguishes our program from most of the other food science programs in the country because we have a strong background in policy and regulation on this campus. Scientific communication in food science, we want to turn you into communicators. You've got to tell the world what you've done. This is true for any scientist, but you have the advantage in food science of having a specialized course in this. And then you can see a whole bunch of other courses, many of which make our program unique in the country. So just so you've got some flavor, I guess that's a pun, of what goes on in food science. Now I want to talk a little bit about nanoscience and our nanotechnology option. And I'll do that by referring to this scale diagram, where down the left-hand side here, we've got a scale in meters. So a centimeter up here, 10 to the minus 2 meters, down to a micrometer down here. An ant is, as you know, a few millimeters, half a centimeter. And the head of a pin, maybe 1 millimeter, something like that. A nice electron image there, of electron microscopic image of it. A human hair, about 60 or around 100 microns wide, about 1/10 of a millimeter in diameter. So you're getting down here to something along the lines of what the human eye can see. Micro electromechanical devices, or MEMS devices, from 10 to 100 microns. So that's from 0.01 to 0.1 millimeters. This is at the limit of what the human eye can see. But this is gigantic compared to the nanoscale. When we look at the nanoscale, we've got to go down many more orders of magnitude. So from 1/10 of a micron down to 1,000th of a micron, which is a nanometer, and even further than that, maybe 0.1 nanometers. So this is the region that we're working in nanoscience and nanotech. Red blood cells, 7 or 8 microns, so that's up at the top of the scale. Those are gigantic. Tracks in an electronic device, tens of nanometers, so way smaller than what you can see. And how small they can make these determines how many transistors they can cram on a chip. That determines how many gadgets they can pack into your cell phone. So your cell phone, I mean, you might think of it as an electronic device, but it's at its heart, it's a chemical device. DNA, about 2.5 nanometers in diameter. So these scales are where we like to work, making devices which work at the nanoscale, where the chemistry is very different from what it is at the microscale or the visible scale. In nanotech, you can actually start a concentration in this in a chemistry degree with a concentration in nanotech in third year. The first 2 years are foundational, and then you get into, for instance, experimental methods in nanoscience, introduction to nanotech, nanostructures and surfaces. Surfaces are very important in nano work. Physical methods of nanotech, and then, as in other chemistry programs, there's what we call a 4908 project. That's a research project and seminar. All of the programs I'm talking about today include that. And that could set you apart from going from students in other universities where they don't have a fourth year project. Potential employers love that kind of stuff. Nanoscience is, as I've said a couple of times, joint between chemistry and electronics. So you're taking courses in both faculties and in both departments. And it's to an end of making microelectronic devices. But the processes used for making these are very much chemical. So we're looking at electronics, photovoltaics, which are things that convert sunlight into electrical energy. Health applications, these would be sensors that they might stick under your skin and it would sense the amount of bicarbonate or whatever in your blood. Tiny, tiny devices. Environmental concerns, so this would also be along the lines of sensing a gas in the atmosphere or a species in water. So all of these are based on nanofabrication. In nanoscience, so this is the joint program between chemistry and electronics, you can see that first year looks pretty similar, chemistry, math, physics, and then there's some other things you've got to take as well in first year. But in second year, you've got to start taking electronics courses as well, because ultimately your goal is to be able to understand and build new electronic devices. This other program, Toxicology, that I said I would talk about, is a fairly new program. And the idea of this is that you learn how and why toxicants exist and why they are toxic in the first place. How do they move through the environment? How do they get into your body? Why are they toxic when they get into your body? What can you do about it to get them out of your body? This sort of thing. This is a pretty big field these days. And so this is a fairly new program, 2 years old at Carleton. You can see first year, pretty familiar, chemistry, biology, physics, math, and maybe some electives. Second year, organic chemistry and biochemistry, very importantly. And then in upper years, more focus on the toxicology aspects. More organic chemistry, chemistry of pollutants, how these pollutants move through the environment. Some more biochem courses, risk assessment, the hazard associated with something, and how much you ingest, and what kind of risk that poses are the subject of that course. And some nitty-gritty courses on environmental chemistry and toxicology. So this is a fairly new program that we're quite proud of. I think many of you would find this of interest as well. Now, what's different about chemistry at Carleton? Why would you come here and not go to U of O? Well, there are a million reasons why you don't want to go to U of O, but if you want to come to Carleton, here's some good reasons to do that. We have high quality teachers here. We're very proud of our teaching. We take teaching very seriously. It's on an equal footing with research in this department. That's how we treat it. Third and fourth year students can be hired as teaching assistants. I think that $22 an hour is a couple of years old, actually. It's probably more like $25 an hour now. Pretty good money. We have some good exchange programs, which would typically happen in third year if you wanted to go away to do some credits abroad, especially with a particular school in France, the École Nationale Supérieure de Chimie in Montpellier. But Carleton International can also arrange and has arranged many exchanges for chemistry students in the UK especially, and in Australia and in the US. And anywhere else in the world you feel like going, but these are fairly popular places. So the teaching is pretty special here. You end up with an excellent undergraduate education. This is one corner of what we call the super lab. I don't know if the dean showed you this, but this is still a relatively new lab. which was designed to house 120 undergraduate students at a time. And that might sound like it's going to be absolute chaos when there are that many students plus a dozen TAs and some lab coordinators in there. It's peaceful and serene, and it just has this buzz of people loving what they're doing chemical experimentation. Half of the lab is for first-year students. The other half is for advanced courses, well, especially organic chemistry. And then there's another lab above this one, half the size, but still pretty substantial size lab, for the senior courses: analytical, environmental, inorganic, and physical chemistry are all run in the senior labs above this one. So we're very proud of our lab facilities. You won't find lab facilities like this in every institution that you visit. I want to mention a couple of other things. Honors programs, those are 4-year programs. They require a 4th-year research project. You have to do a 4th-year research project. It's under the supervision of one of us, one of the faculty members, but you're expected to do something novel. And to do that, you've got to work independently, still as part of a team, but a lot of what you do has to be done independently. And it's your first real stab at independent research. And this has to be defended in front of a panel of professors when you're done. I mean, it might sound a bit intimidating. It's not. We know where you're coming from. We know what you are able to do. You can do this if you're in 4th year. But this is something that you can hold up when you go looking for employment. I did independent research in 4th year, and you can show them. I'll show you one right here. I've got a whole bunch of them on my bookshelf. You can show them your 4th year project, which is written up like a thesis, because it is a thesis. This is 50 pages of writing. This one was done quite a long time ago, 1995. I've had a lot of these students in my labs over the year. So you can prove to somebody that you've done independent research because you've written a thesis like that. In order to sort of roll you into the fray, as it were, to get you to be one of us, we start in 1st year. And I mentioned that natural science seminar that only has 30 students per section. We try and knit you together as a group. And we want you to have a collegial association with one another, with our staff members, and with the faculty members like me. My door here is literally, and I know people say the door's always open. The door is literally open all the time, and students are coming in and out routinely. We also have an active student chapter of the Canadian Society for Chemistry, or the Chemical Society of Canada, as it's called. That student chapter arranges tours of local industries. They have social events. They have career nights, and so on. So that's a great thing to join. All of our students join. It costs $5 to join. And then you get cheap pizza and beer as well. So-called liquids dynamics labs, where we study how beer percolates down through your body, basically. We have those once a month or something like that. Other things that are special about chemistry here: we want chemistry to be educational, of course, that's what you're paying for, but we want it to be entertaining and fun as well. So we do a number of magic shows per year, sometimes 2 or 3 magic shows per year. Stupid COVID has sort of nixed them for the last year and a half, but we are going to have one this December. And we need, it says 30 student volunteers here. We actually need more like 50 student volunteers, because we bring 1,200 people onto the campus to see these magic shows, where we set things on fire and blow stuff up and make it cold, make it hot, make it change color, and so on. We have a lot of fun doing these. Here is our nighttime outdoor magic show, which happens in May. You can see, I guess that's me crouching down here. This is called a thermite reaction, which is just fun. This is a chemical reaction, which is hot enough to melt iron. So we can do things on a big scale when we do them outdoors at nighttime. It's just, it's a lot of fun. Here's somebody else with a glow-in-the-dark experiment. So we like it to be fun and entertaining as well. Well, that's all I have to say, I think, about our programs. I would invite any questions that you have to be thrown into the chat. I don't know if you have the ability to speak into a microphone too. Feel free to do either of those things. I'm happy to answer any of your questions. Cat's got your tongue, right? This is usually the case for first-year students. They turn off their cameras and they turn off their microphones. I know you're listening, but it's nice to hear back from you as well. Let's see who else we have here. We've got people from Canada, Colombia, Canada, Dominica, Canada, and Canada. So mostly Canada, but two from outside the country as well. So I'm done speaking, but I'd love to answer any questions you have. No questions. You gotta have questions. Come on. Don't be shy. I'll turn my camera over there. You can see all those blue and red and green books. Those are all student theses. Theses of students that have done work in my labs over the years. So I want to emphasize again that that's a very big part of what you do here, is get into the research labs and finish off by doing this independent research project. The green books are fourth year student projects. The red ones are master's students, and the blue ones are PhD students. So a lot of people stay a little longer, do a few more years, a few more degrees, and get that advanced degree. Not really what we're talking about today. You got to start with your bachelor's degree. But what's the retention rate for chemistry in first year? That's a great question, Sydney. The retention rate is very high. I mean, science-wide, it's about 85%. In chemistry, it's about 90% retention. And those who leave, it's not because they couldn't handle it. It's because they're on a campus and they happen to take a course in Italian literature as their arts elective in first year, and they simply decided they would prefer to study Italian literature than chemistry. So when you're on campus, you should do these things. You should take courses in other areas, because it's sort of your last chance to discover, first and last chance to discover what you love to do. Anyway, the retention rate is very high, and it's also partly because we're watching you very carefully. We want to meet you and know you, and if we see that you're having difficulties anywhere, we want to help you. We don't want to whack you and give you a low grade. What we want to do is help you learn so you get good grades. You probably heard that sort of thinking in the Dean session too, where they talked about the Science Student Success Center. And if we perceive any weakness, well, we step in there and we try to help you. It's not a punitive thing at all. It's in an attempt to assist. What else do you have to ask me? What else can I tell you? I can tell you that I've been here for 46 years. I came here as a first-year student. So when I say that I know what it's like to be a first-year student, I mean, I'm having trouble remembering maybe, but I was here. And so I know the issues, and I know how to mitigate them. I think Carleton's the center of the universe. I had a real job for about 5 years, but otherwise I've been here my entire life. That's how much I love the place. You would too if you came here. And that's not just a pitch. I'm telling you that from experience. It's just a wonderful place to be. Glad that it was helpful, Lisa and Rebecca. Would it be possible to study a double major in chemistry and math? So it's not called a double major, but it's very common to study chemistry and math together. And the way it's done is to take a major in chemistry and do a minor in math. So a minor, you can do any minor from any major, essentially. A major is 20 credits across the 4 years, and a minor is an extra 4 credits. So if you were to take these, in the usual 5 credits per year, This adding a minor in math would add an extra year to your studies, but you have to do a lot of math in chemistry already. You've got to do 2 credits, so there's half of your minor already. And then you can take extra math courses, which will satisfy your electives in your chemistry program, but also satisfy the math minor. So it's possible to do a math minor without doing any extra credits, is what I'm saying. And it's a very powerful 1-2 punch if you're on the sort of physical side of chemistry. I would strongly urge you to take more math. And if you love math and you love chemistry, boy, that's just a great combination. And you can do it within the 20 credits. So you could, even take more credits than that if you wanted to. Many students take so-called credits extra to the degree simply because they feel that they want to know this information. They want to be stronger in math than they were. So they actually do more credits than are required to get the degree. But to answer your question directly, it's not a double major. It would be doing a major in one plus a minor in the other, plus additional courses if you wanted to. But very common in chemistry. That's probably the most common minor to do in chemistry is a minor in math. That and a minor in biology. Because the two, the chem and bio or chem and math, they go hand in hand. So doing a little extra, get you an extra annotation on your degree. A minor in food science is also quite common because people are curious about food science. We're all interested in food. And so they're curious about food science, so they do a minor in food science. And that's possible to do from a degree in chemistry as well. Well, you can do a minor in almost anything. But math and food science and bio, those would be the 3 most common from a chemistry degree. You could also, if you wanted to do computer science, you could also do a minor in chemistry. It works both ways. So I hope that's been of use to you. Apparently we're going to get thrown out of our room in a couple of minutes. If you want more information, you can certainly get it by emailing chemistry@carleton.ca, and we'd be delighted to give you whatever information you need. I know it's easy to find information on the web these days, but if you want to talk to somebody or if you want to come and see us, by all means, if you're in Ottawa or if you're going to pass through Ottawa, just get in touch with us. We'd be delighted to give you a tour of the building. We had an on-campus tour last weekend. Yours is the virtual tour, so I'm guessing that means that you're not in the city. But if you are in the city or if you're coming through the city, let us know. We'd be delighted to show you the labs and introduce you to the people and the programs in this department. Can you transfer credits if you're coming in with an associate degree? Yes. Any credit that you bring from another accredited institution gets examined by me, in fact, if it's a chemistry course, and we decide that, well, that course that you're bringing in, that looks like our Chem 1002. So we give you credit for it if you come here, and you don't have to do it again. So any credits that you're bringing in, not high school credits, but above high school credits, absolutely. Give us the documentation. We will examine them and determine if we have an equivalent course. If we do, we give you credit for it here. So it's done not just by degree, but by course. All right, looks like we're about to get kicked out. Thanks for coming, everybody, and thanks for your questions. Sure hope we'll see you here.